January 8th, 1998. Freezing rain had been falling across southern Quebec for 4 days, and the ice weight on the conductors of a 230 kilovolt transmission line had exceeded what the cables were designed to carry. The conductor let go in the early morning. When it struck the ground, 230,000 volts found Earth in a fraction of a second. The current spread outward from the contact point through the soil in all directions, following every path available. The voltage difference between 2 points on the ground, 1 step apart, 3 feet apart, was lethal to any person standing within 60 feet of where that wire landed. A cow standing in a field 40 feet from the contact point would have died before it fell. No visible arc, no sound from the ground, no heat at the perimeter, just soil carrying enough current to stop a heart, only on a wire lying in the grass. This is the story of step potential, the hazard built into the physics of every high-voltage transmission line failure. The engineers who quantified it decades before a formal safety standard existed, and the gap between what was published in electrical engineering journals and the farmer who walked toward a downed conductor to move it out of his driveway. If this is the kind of engineering history you come here for, subscribe now. A 150 kilovolt transmission conductor is aluminum wound around a steel core. The industry designation is ACSR, aluminum conductor steel reinforced. The steel carries the mechanical load, the aluminum carries the current. The design solves a problem that the first long-distance transmission engineers struggled with from the beginning. Steel is strong but resistive. Aluminum is conductive but weak, and neither material handles the mechanical demands of spanning 1,000 to 1,500 feet between towers without the other. Together, an ACSR cable can carry 500 amperes at 150,000 volts across 200 miles of mountain terrain with line losses under 3%. That is approximately 75 megawatts of power, enough for 50,000 homes, moving through a cable roughly an inch in diameter. The line hangs between lattice steel towers 80 to 120 feet tall. Between towers, the conductor hangs in a catenary curve, and the lowest point of that curve, the midspan sag, is engineered to maintain at least 25 feet of ground clearance at the highest expected conductor temperature. Heat expands the aluminum and increases sag. On a hot summer afternoon at peak load, a conductor can sit 4 feet lower than its winter position. At 150 kilovolts, a conductor approaching a tree, a vehicle, or a person at less than 10 feet can arc without contact. Air breaks down at roughly 1,000 volts per millimeter of gap. The clearance standards in the National Electrical Safety Code are not conservative engineering buffers. They are the thresholds below which reliable operation cannot be guaranteed. The insulators connecting each conductor to the tower are porcelain or tempered glass discs, each rated for 15 kilovolts, stacked 10 to 12 in series for a 150 kilovolt line. They are designed to a safety factor of 3 against electrical failure. The tower attachment hardware is designed to a factor of 5 against the maximum expected ice and wind load. What those factors mean in practice is that the line will survive everything short of an extreme event. Ice storms, yet coincident high wind events, and large tree falls are extreme events. They occur regularly across the regions where transmission lines run. When one of them occurs at the right time in the right place, the conductor falls. What happens on the ground after that is what the rest of this script is about. If you want more engineering history like this, the physics underneath the failures, subscribe. This is what we do here. When a 150 kilovolt conductor contacts Earth, the fault current that flows depends on the transmission system's impedance and the soil resistance at the contact point. On a typical 150 kilovolt system with substations within 50 miles, fault current can reach 10,000 to 20,000 amperes. That current enters the soil at the contact point and radiates outward in all directions. The voltage at the contact point rises sharply, briefly near the full system voltage, and drops as the current spreads and the soil resistance increases with distance from the fault. The drop is not linear. Voltage falls steeply in the first few meters and then flattens. The gradient, volts per meter of ground, is highest at the center and becomes shallower with distance. Step potential is the voltage difference across 1 meter of ground measured in the direction of the steepest gradient. A person standing with one foot 20 feet from the contact point and the other foot 21 feet away is bridging that 1 meter potential difference. At 150 kilovolt fault current levels and typical soil resistivity values measured in the field, step potential at 20 feet can exceed 2,000 volts across that 1 meter gap. At 15 feet, it is higher. The human body in a standing position, current flowing foot to foot through the lower legs and across the pelvis, presents roughly 1,000 to 2,000 ohms of resistance through skin and soil contact. At 2,000 volts, that path drives 1 to 2 amperes through the lower body. Ventricular fibrillation in a human being requires 100 milliamps through the chest, sustained for more than 1 second. The step potential current at a 150 kilovolt fault site exceeds that threshold by a factor of 10 to 20 at distances where there is no visible arc, no audible warning, and no reason to believe the ground itself is the hazard. Animals with 4 legs are more vulnerable than humans for a specific geometric reason. A cow standing broadside to the voltage gradient bridges a far longer step distance than a standing person. Either one front foot and the diagonal rear foot can be on opposite sides of a voltage contour, placing the fault current path directly through the animal's chest across the heart. In documented agricultural extension reports and OSHA utility fatality case summaries, cattle have been found dead in fields with no external injuries and no sign of direct conductor contact. The only evidence is a conductor on the ground and a spatial pattern of deaths clustered within 60 feet of the contact point. Calves and horses, with shorter legs and lower body impedance to soil, die at greater distances from the fault. The protection relay at the substation detects the fault current and trips the line breaker. On a modern digital relay system, that trip happens in under 100 milliseconds. On older electromechanical equipment, it takes 200 to 300 milliseconds. Say after the trip, the system automatically reclosed, sent voltage back onto the line to test whether the fault had cleared. A tree branch that briefly contacted the conductor and burned off would allow the reclose to succeed. A conductor still lying on the ground would not. Older automatic reclose systems cycled 3 times before locking out permanently, with 15 to 30 seconds between each attempt. 3 separate pulses of full fault current, each up to 300 milliseconds long. A person approaching a downed conductor after the first trip, seeing a wire that appeared dead, hearing no arc, feeling no shock from the ground at the distance where they stopped, could be killed by the second or third pulse while still in what they understood to be a safe position. The physics of ground current around a fault point follows directly from equations James Clerk Maxwell published in completed form in 1865. Current flowing from a point source into a resistive medium creates a voltage gradient around that point. The mathematics does not change whether the medium is air or soil, whether the source is a lightning strike or a transmission conductor. Every electrical engineer who trained in the late 19th century and worked on the first AC transmission projects understood the theory. The question of when that theory was turned into safety standards is a separate question entirely. The first long-distance AC transmission ran 175 kilometers from Laufen am Neckar to Frankfurt, Germany in 1891 at 25 kilovolts. The Niagara Falls to Buffalo project of 1895 used 11 kilovolts to move power 26 miles, and settling the war of currents in favor of alternating current and Westinghouse's AC system over Edison's direct current distribution. That project established the commercial model: step voltage up at the source, transmit at high voltage with low losses, step it back down at the destination. The economics of that model pushed transmission voltage relentlessly upward through the following decades. By 1910, experimental lines in California were running at 110,000 volts. By 1920, 220,000 volt lines existed. The voltage went up because higher voltage meant lower current for the same power, and lower current meant smaller conductors and fewer losses over long distances. The safety standards did not track voltage at the same rate the voltage tracked commercial demand. The first systematic treatment of step potential and touch potential as formal engineering design problems appeared in American electrical engineering literature in the 1940s, applied specifically to substation grounding grid design. The Institute of Electrical and Electronics Engineers published Exterioricidades Itidae Standard 80, covering ground grid design for substations in its first formal version in 1961. That standard contained explicit calculations for step potential and touch potential, defined lethal current thresholds through the human body based on weight and current duration, and specified the grounding grid designs that dissipate fault currents safely around transformer yards and switchgear. It was written for substation designers. It reached the engineering community that specified enclosed, secured electrical infrastructure. Then it did not reach the public, and it did not reach the worker clearing storm debris on a rural road. OSHA's 1910.269 Standard for Electric Power Transmission and Distribution Work, first issued in 1994, made step potential a required training topic for utility workers. The standard required workers to know the approach distances for downed conductors as a function of line voltage, to understand that automatic reclose could re-energize a line that had been tripped, and to use what the standard called the shuffle step technique when moving near a fault location. Feet kept close together, never fully lifted from the ground, minimizing the voltage difference across the current path. The shuffle step minimizes step potential exposure by keeping both feet at nearly the same equipotential contour. It had been an informal practice among experienced linemen for decades before OSHA codified it. The 1994 standard reached utility workers. The general public received a simplified version of the same information starting in the 2000s through utility safety campaigns. Stay back 60 feet from any downed conductor and call the utility company. 60 feet is the number because it represents the distance at which step potential from a 150 kilovolt fault, under worst-case assumptions for soil resistivity and fault current magnitude, drops below the threshold that produces reliable ventricular fibrillation in a healthy adult. It is not a generous margin. It is based on field measurements and incident data. In wet soil, conductive clay, or standing water, the ground current spreads further and the lethal radius extends. If the 60-foot figure was adopted as public guidance because any defined number is better than none, and the utilities settled on the value that covered most conditions without being so large that it lost credibility. In the conditions it does not cover, it is not enough. Between January 4th and January 10th, 1998, freezing rain fell continuously across eastern Ontario, Quebec, and northern New England. Ice accumulated on transmission conductors at 2 to 3 times the design loading standard for the Hydro-Quebec transmission system. The 735 kilovolt backbone lines that carry power from the James Bay hydroelectric generating stations to Montreal and Quebec City are designed for approximately 0.4 inches of radial ice on the conductor. The 1998 storm deposited 2 to 3 inches of radial ice across 200 kilometers of line. Now, over 1,000 steel transmission towers collapsed in Quebec. The conductors came down across farm fields, rural roads, driveways, and residential streets in a region where 3 million customers lost power. The lines that failed first were not the 735 kilovolt backbone. The backbone held longer because the towers are heavier and the spans shorter. The lines that failed earliest were the sub-transmission lines, the 120 kilovolt and 230 kilovolt circuits that move power from regional substations to local distribution networks. These are lines of the voltage class where step potential produces the geometry this script has described. 35 people died in Canada and 17 in the United States as a direct consequence of the storm. The official fatality breakdowns included carbon monoxide poisoning from improper generator use, house fires from alternative heating, and hypothermia. The number of deaths attributable to electrical contact from downed conductors was not cleanly separated in the published summary reports. What the OSHA utility fatality data from the 1998 to 2000 period shows is a documented increase in public electrical contact fatalities during and following major ice storm events, including several cases where contact occurred not at the conductor, but at a distance from it, through the ground. The conditions that produced the 1998 damage were not unpredictable. The Hydro-Quebec system had been built to loading standards derived from historical weather data for the region. The 1998 storm fell outside those historical parameters. A review published by the Electric Power Research Institute after the storm concluded that the loading standards for transmission infrastructure in the northeastern United States and eastern Canada had been set based on weather records that did not include the full range of freezing rain severity that the region was capable of producing. The recommendation was to revise loading standards upward. Revision of those standards across the existing transmission network would require replacing towers, reconductoring lines, and rebuilding attachments across tens of thousands of miles of infrastructure at a cost the review estimated in the hundreds of billions of dollars over 20 years. The recommendation was noted. The infrastructure remained largely unchanged. The United States operates approximately 700,000 miles of high-voltage transmission lines. The average age of that infrastructure is over 40 years. The design life of a lattice steel transmission tower is 50 to 80 years with regular maintenance. Maintenance spending on transmission lines contracted through the 1990s and 2000s as federal deregulation restructured the power industry, separating the companies that generate electricity from the companies that own the transmission wires. Wire owners faced pressure to reduce operating costs while maintaining regulatory uptime requirements. Inspection cycles lengthened. Maintenance on aging hardware was deferred. The wires continued to carry 150,000 volts over countryside, through farmland, and across suburban development that in some cases had grown up around transmission corridors built decades earlier when the surrounding land was empty. NOAA and the Electric Power Research Institute both project increases in the frequency of extreme precipitation events, including freezing rain events at the severity of the 1998 storm across the northeastern United States through the coming decades. Warming shifts the precipitation temperature distribution toward the range that produces freezing rain rather than snow in regions that historically received snow. Freezing rain loads on conductors are heavier than snow loads for equivalent precipitation. A line designed for 0.4 inches of radial ice that sees 1.5 inches will fail. The tower will buckle or the conductor will part, and the contact point voltage gradient will be determined by fault current magnitude and soil conditions, not by the age of the tower that failed. The 2003 Northeast blackout, the largest in North American history, began with a software failure in an Ohio Utilities energy management system that allowed three 345 kilovolt transmission lines to sag into trees and fault to ground in sequence during a high-load summer afternoon. 55 million people lost power across 8 states and southern Ontario. The lines that faulted were in rural areas, the fault clearing was fast, and no deaths from step potential were attributed to those specific faults. Where the cascade that followed the faults, the sequential tripping of interconnected transmission circuits across the northeastern grid, demonstrated that a transmission failure in one location can propagate through thousands of miles of interconnected infrastructure within seconds. The grid's interconnection, which is the feature that allows power to move from generating stations to distant load centers, is also the mechanism that allows a local fault to become a regional outage. Those two properties cannot be separated.